Hello there and welcome to the second video on binary trees. Hopefully by now you can traverse binary tree structures. In this video we're going to be looking at building binary tree structures and then traversing them and then finally converting them into two-dimensional arrays. So have a look at this question, pause the video and give it a quick read if you need to. This is the 2016 Specimen Assessment Material question from Educas. The first question gives you rules based on building a binary tree. The first rule states that the first item becomes the root node. Rule 2 states that items earlier or at the same position in the alphabet follow the left pointer, and Rule 3 states that items later in the alphabet follow the right pointer. Now my students like to write down the alphabet for this so that they don't make mistakes. It's very, very easy under the stress and pressure in an exam to make very simple mistakes and lose easy marks here. So be very, very careful. Let's have a look at question 1A. Draw a representation of a dynamic binary tree with pointers using the following data: Newport, Canterbury, Oswestry, Warrington, Rugby, Bath and Derby. Now this question's worth 2 marks. All we have to do is build the binary tree based on the rules given. So let's have a go. The first thing to denote from this question is the first item in the list is going to be the root node. So that means Newport is going to be the root node of my binary tree. And to model what my students do, I'll quickly write the alphabet at the top because this will help us keep on track with the nodes that we're adding to our binary tree. The next item to add in is Canterbury. Canterbury comes before Newport, N, in the alphabet, and therefore it's going to go to the left of the root node. The next node in my list is going to be Oswestry. Starting at the root node again, I'm going to look at O. O comes after the letter N, and therefore we are invoking rule number 3 and moving to the right pointer. So we add it to the right of Newport. Then looking at Warrington, we're going to look to the right of Newport. Then we get to O. We compare O and W together. W comes after O, and therefore Warrington goes to the right of Oswestry. Then we look at Rugby. We compare R and N. R comes after N, so we move to the right. We compare R and O. R comes after O, so we move to the right again. And then we compare it to W. O comes before W in the alphabet, and therefore we move it left and we place Rugby to the left of Warrington. The next one on our list is Bath. We compare N with B. B comes before N in the alphabet, so we move left. We compare it with C. B comes before C in the alphabet, so we go left again and we place Bath to the left of Canterbury. Finally, we look at Derby. Derby comes before N. It comes after C, and therefore it goes to the right of Canterbury. In question 1B, we need to show how the tree could be represented using a two-dimensional array. So we have to think about this carefully because a binary tree is a different data structure than a two-dimensional array. However, we can hold the information from a binary tree inside a two-dimensional array if we think about it as if a binary tree had 3 things: a left pointer, a right pointer, and the data itself. The only thing the two-dimensional array will be storing is the left pointer number and the right pointer number, because don't forget, a binary tree can only hold one data type. Therefore, it wouldn't be appropriate for this data structure to store the data. So I'm going to draw a table to represent this. My table will have all the data from question 1A in the middle column. So I'll add Newport, Canterbury, Oswestry, Warrington, Rugby, Bath and Derby. Newport will be position 0, Canterbury will be position 1, Oswestry will be 2, Warrington 3, Rugby 4, Bath 5 and Derby 6. And I'll draw that on my tree to help you see what I'm talking about here. And all I have to do for question 1B is show which pointers are connected to what data. So for example, Newport has a left pointer of Canterbury. Canterbury has the numerical value of 1. Oswestry has the numerical value of 2. So the left pointer is 1 and the right pointer is 2. Then I move down to Canterbury. Canterbury has a left pointer of 5 and a right pointer of 6. Oswestry has a left pointer of -1. Now I use -1 to say null, or there's nothing connected to it. And then Oswestry points to number 3, which is Warrington. So its right pointer is 3. Warrington then has one item to its left, which is Rugby, at position number 4. And to its right, it has nothing. So I write -1. Rugby then has no children, so they're both -1, as does Bath and Derby. And that's how we represent a binary tree structure in a two-dimensional array. Question 1c asks us to make amendments to the tree represented as a two-dimensional array. So the first one asks us to insert new key into the tree. Now what I'm going to do is I'm going to actually add it to my diagram, because then it will be nice and simple for us to add it to our two-dimensional array. So the first thing, let's have a look at where new key sits in our binary tree structure. Now have a look at rule number 2. Rule number 2 states that items earlier or at the same position in the alphabet follow the left pointer. So we look and see N is the same as Newport, E for new key is the same as the E for Newport, the W is the same, therefore now we're looking at the fourth letter. The P for port and the Q for key. Q comes after P in the alphabet and therefore new key sits to the right of Newport. Then we look at Oswestry. N comes before O in the alphabet and therefore new key moves to the left of Oswestry and there's no child there, so we place it in that position. Once placed in the correct position, I'll give new key the number 7 and that's its identifier. We'll add that then to our table. But before I do that, I'll just take a quick look at the second question. While I'm in the table, I'm going to delete Warrington from the tree. Now, as we saw in the previous video, I'll cross Warrington out and I will change the pointer from Rugby to Oswestry. Now I've done all of that in my diagram, I need to make sure that my table reflects exactly what I've done in my diagram. So to do this, I'm going to add new key to my table and give it the ID of 7. I'll give its left pointer -1 and its right pointer -1 because it doesn't point to anything. I'll change Oswestry's left pointer to 7 and Oswestry's right pointer to 4. And that's simply because I've deleted Warrington and I need to change its pointer. So what about question 1D? Give one advantage and one disadvantage of using a binary tree to store data compared with a linked list. Now, the key difference between a linked list and a binary tree structure is that a linked list has data but only one pointer, whereas a binary tree will have a node which may contain the data and 2 pointers from that. So the advantage with binary trees is that you have faster searching. We've just looked at a pre, post and in-order traversal in the previous video, and that's one major advantage of a binary tree structure. On the other side, the disadvantages are the memory overheads. For every node, we can have a possibility of 2 pointers, and each one of those pointers could be connected to a node which also has 2 pointers, and it can keep going and growing exponentially. So the problem is with the memory of having multiple pointers. And also, when you create the algorithm and you access it, the pre, post and in-order traversals, usually they are more complicated to implement, as is the binary data structure itself. So there's a couple of disadvantages for you for that question. The final question, 1E for 4 marks, giving examples, compare a balanced and unbalanced binary tree and evaluate their effectiveness to solve problems by comparing the maximum number of comparisons to locate an item in each of these trees. So if we think about a balanced tree and an unbalanced tree and what that looks like, I'm going to use the same number of nodes to show this. As you can see, I've got a perfectly balanced binary tree on the left, and on the right I've got an unbalanced binary tree with no left subtree. Think about the number of comparisons if we were to search through these trees. On the left I've only got maximum of 2 levels to search through, whereas on the right I have to search through all 3 levels here. And that's one more than I ideally would like to be searching through. If we were searching through a binary tree, for example, and it was fully balanced, then that would be absolutely fantastic because I can use things where I can search through and compare the middle or the root node and then work out if my item is greater than or less than the root node. I can disregard 50% of the tree, potentially 50% of the tree, each time I go along, which is much more efficient than my unbalanced tree. And that's all the question is actually getting at here. As long as you have given correct examples and you've explained your point thoroughly, then you should get all 4 marks in this question. And that's a quick look at one question on binary trees. Don't forget that you could be expected to compare binary trees with any other data structure in this specification. Again, I'd just like to say thank you very much for listening, and hopefully you'll join me for the next video.